The story of pressurized cabins begins not in the skies, but on the ground, where early aviators first grappled with the challenges of flight. In the early 20th century, as humans took to the air in fragile, open-cockpit biplanes, the primary concerns were stability, propulsion, and basic survival. These pioneering aircraft rarely climbed above 10,000 feet, as the thin air at higher altitudes posed significant risks to both pilots and passengers. The atmosphere, so familiar and life-sustaining, at ground level becomes increasingly hostile as one ascends. At 18,000 feet, the air pressure is roughly half of what it is at sea level, and by 30,000 feet, a common cruising altitude for modern jets, the pressure drops to less than a quarter. Without adequate protection, humans cannot survive for long. In such conditions, the human body is finely tuned to function within a narrow range of atmospheric pressure. At high altitudes, the reduced oxygen levels lead to hypoxia, a condition where the brain and other vital organs are deprived of the oxygen they need to function. Symptoms of hypoxia include dizziness, confusion, and, in severe cases, loss of consciousness. Early aviators, often flying without oxygen masks, experienced these effects firsthand. Some described euphoric sensations, while others recounted terrifying moments of disorientation. The dangers were clear. Without a solution, the dream of long-distance, high-altitude flight would remain out of reach. As aviation technology advanced, so did the ambition to fly higher and faster. Higher altitudes offered smoother air, reduced drag, and greater fuel efficiency, all of which were essential for the development of commercial aviation. However, the human body's limitations remained a formidable barrier. The first attempts to address this problem were rudimentary. Pilots began using oxygen masks, which allowed them to breathe supplemental oxygen at high altitudes. While this was a significant improvement, it was far from a comprehensive solution. Oxygen masks were uncomfortable, cumbersome, and impractical for passengers. Moreover, they did nothing to address other physiological challenges, such as the expansion of gases within the body, which could cause severe pain or even injury. The breakthrough came with the realization that the entire cabin environment needed to be controlled. Instead of relying on individual oxygen masks, engineers envisioned a system that would maintain a stable, breathable atmosphere inside the aircraft, regardless of the external conditions. This concept, known as cabin pressurization, would revolutionize aviation. The first successful implementation of cabin pressurization occurred in the 1930s, with the development of the Boeing 307 Stratoliner, the first commercial aircraft with a pressurized cabin. This innovation marked the beginning of a new era in aviation, one where passengers could travel comfortably and safely at altitudes previously considered inhospitable. The science behind cabin pressurization is both elegant and complex. At its core, the system works by compressing air from the aircraft's engines and pumping it into the cabin. This compressed air creates an artificial atmosphere, maintaining a pressure level equivalent to an altitude of around 6,000 to 8,000 feet, even as the plane soars at 30,000 feet or higher. The process is carefully regulated by a series of valves and sensors, which ensure that the pressure remains within safe limits. If the pressure drops too low, oxygen masks deploy automatically, providing a backup supply of breathable air. The benefits of cabin pressurization extend far beyond passenger comfort. By maintaining a stable internal environment, pressurized cabins protect against the physical stresses of high-altitude flight. They prevent the painful expansion of gases in the body, reduce the risk of hypoxia, and shield passengers from the extreme cold of the upper atmosphere. Additionally, pressurization allows aircraft to operate more efficiently, as they can fly at optimal altitudes without compromising safety. Yet the development of pressurized cabins was not without its challenges. Engineers had to overcome significant technical hurdles, including the need to design aircraft structures that could withstand the constant stress of pressurization and depressurization. The fuselage in particular had to be reinforced to prevent catastrophic failure. Early pressurized aircraft were prone to leaks and other mechanical issues, which required ongoing refinement and innovation. Over time, advancements in materials science and engineering led to the creation of stronger, more reliable aircraft capable of sustaining pressurized environments over long distances. The introduction of pressurized cabins also had profound implications for the aviation industry. It enabled the expansion of commercial air travel, making it possible to transport large numbers of passengers across vast distances with unprecedented speed and comfort. Airlines could now offer flights that were not only faster, but also more enjoyable, attracting a broader audience and transforming air travel from a luxury into a commonplace mode of transportation. The psychological impact of this shift cannot be overstated. For the first time in history, ordinary people could traverse continents and oceans in a matter of hours, experiencing the world in ways that were previously unimaginable. As the first scene of this exploration draws to a close, it is clear that the development of pressurized cabins was a pivotal moment in the history of aviation. It was a triumph of human ingenuity, born out of necessity and driven by the relentless pursuit of progress. The challenges of high-altitude flight were formidable, but through innovation and determination, they were overcome. The pressurized cabin stands as a testament to the power of science and engineering, a solution that has shaped the modern world and continues to enable the wonders of air travel. Yet, this is only the beginning of the story. The science of cabin pressurization is a rich and multifaceted topic encompassing principles of physics, biology, and engineering. In the scenes to come, we will delve deeper into the mechanics of pressurization, explore the physiological effects of high-altitude flight, and examine the ongoing advancements that ensure the safety and comfort of passengers in the skies. The journey is far from over, and the skies still hold many secrets waiting to be uncovered. The marvel of cabin pressurization lies not just in its concept, but in the intricate engineering that makes it possible. To understand how an aircraft maintains a breathable, comfortable environment at 30,000 feet, one must first grasp the fundamental principles of atmospheric pressure and the challenges of replicating it within a metal tube hurtling through the sky. The process begins long before the aircraft takes off, embedded in the design and construction of the plane itself. Modern commercial aircraft are essentially cylindrical pressure vessels designed to withstand the immense forces exerted by the difference between the internal and external pressures. The fuselage, the main body of the aircraft, is constructed from lightweight yet incredibly strong materials, typically aluminum alloys or advanced composites. These materials are chosen for their ability to endure the cyclical stress of pressurization and depressurization, a phenomenon known as fatigue. Each flight subjects the fuselage to significant strain as the cabin is pressurized during ascent and depressurized during descent. Over thousands of flights, this repeated stress could weaken the structure, making durability a critical consideration in aircraft design. The heart of the pressurization system lies in the aircraft's engines. As the engines generate thrust, they also produce a byproduct essential for cabin pressurization: compressed air. This air, known as bleed air, is siphoned off from the engine's compressor stages before it mixes with fuel for combustion. At high altitudes, where the outside air is too thin to breathe, this bleed air becomes the lifeblood of the cabin environment. It is hot, dense, and rich in oxygen, making it ideal for maintaining a stable atmosphere inside the aircraft. Once extracted, the bleed air is routed through a series of ducts and valves to the Environmental Control System, ECS, the brain of the pressurization process. The ECS is a sophisticated network of components that regulate the temperature, pressure, and humidity of the cabin air. One of its key functions is to cool the bleed air, which can reach temperatures exceeding 200 degrees Celsius. This is achieved through heat exchangers, which use outside air to reduce the temperature of the compressed air before it enters the cabin. The cooled air is then mixed with recirculated cabin air, creating a comfortable and breathable environment. The pressurization process is carefully controlled by an onboard computer system, which monitors and adjusts the cabin pressure in real time. The target pressure is typically equivalent to an altitude of 6,000 to 8,000 feet, a range that balances passenger comfort with structural safety. Maintaining this pressure requires a delicate equilibrium. As the aircraft climbs, the outside air pressure drops, and the pressurization system must work harder to maintain the desired internal pressure. Conversely, during descent, the system gradually reduces the cabin pressure to match the increasing external pressure, ensuring a smooth transition for passengers. A critical component of the pressurization system is the outflow valve, a mechanism that regulates the flow of air out of the cabin. By adjusting the size of the valve, the system can control the rate at which air escapes, thereby maintaining the desired pressure. The outflow valve operates in tandem with the aircraft's altitude, opening wider during ascent to release excess pressure and closing during descent to retain air. This dynamic process is automated, with the onboard computer making constant adjustments to ensure stability. Despite the sophistication of modern pressurization systems, they are not infallible. One of the most dramatic risks is a sudden loss of cabin pressure, known as decompression. This can occur due to structural damage, such as a breach in the fuselage or a malfunction in the pressurization system. When decompression happens, the cabin pressure drops rapidly, mimicking the thin air of high altitudes. In such scenarios, oxygen masks deploy automatically, providing passengers and crew with a temporary supply of breathable air. Pilots are trained to respond immediately, initiating an emergency descent to a lower altitude, where the air pressure is sufficient for survival. The engineering behind cabin pressurization is a testament to human ingenuity, but it is also a reminder of the delicate balance required to sustain life in the skies. Every component, from the fuselage to the outflow valve, plays a crucial role in creating a safe and comfortable environment. The system's reliability is a product of decades of refinement, driven by lessons learned from both successes and failures. One such lesson came in the form of the de Havilland Comet, the world's first commercial jet airliner. Introduced in the 1950s, the Comet was a groundbreaking aircraft, featuring a pressurized cabin that allowed it to fly higher and faster than its predecessors. However, a series of catastrophic failures revealed a critical flaw in its design. The square windows of the Comet created stress points that over time led to metal fatigue and structural failure. These tragedies underscored the importance of meticulous engineering and rigorous testing, principles that continue to guide aircraft design today. The evolution of cabin pressurization has been shaped by both technological advancements and a deepening understanding of human physiology. Early systems were rudimentary, often struggling to maintain consistent pressure and temperature. Today, thanks to innovations in materials science, computer technology, and aerodynamics, pressurization systems are more reliable and efficient than ever. They are also more adaptable, capable of adjusting to a wide range of conditions and ensuring passenger comfort on flights of all durations. As the second scene of this exploration concludes, the complexity of cabin pressurization comes into sharp focus. What began as a simple idea maintaining a stable atmosphere inside an aircraft, has grown into a highly sophisticated system that integrates physics, engineering, and biology. It is a system that operates quietly in the background, unnoticed by most passengers, yet it is fundamental to the safety and success of modern aviation. In the next scene, we will delve into the physiological effects of high-altitude flight and the ways in which cabin pressurization protects the human body. From the risks of hypoxia to the mysteries of decompression sickness, the journey through the science of the skies continues, revealing the intricate interplay between technology and biology that makes air travel possible. The story of cabin pressurization is not just one of engineering marvels. It is also a tale of human physiology and the remarkable ways our bodies adapt or fail to adapt to the challenges of high-altitude flight. At the heart of this narrative is a simple yet profound truth. The human body is exquisitely tuned to function at sea level, where the air is dense and oxygen abundant. As altitude increases, the rules change, and the body must contend with an environment that is increasingly alien and hostile. The primary challenge of high-altitude flight is hypoxia, a condition caused by insufficient oxygen in the bloodstream. At sea level, the atmosphere contains approximately 21% oxygen, a concentration that supports the metabolic needs of the human body. However, as altitude rises, the air becomes thinner and the partial pressure of oxygen decreases. By $10,000 feet, the available oxygen is significantly reduced, and by 18,000 feet, it is barely enough to sustain consciousness. At the cruising altitude of a commercial jet, around 30,000 to 40,000 feet, the external oxygen levels are so low that unconsciousness can occur within seconds. The effects of hypoxia are insidious and often go unnoticed until it is too late. Early symptoms include lightheadedness, euphoria, and impaired judgment, which can lead to dangerous decisions. As oxygen deprivation worsens, vision blurs, coordination falters, and cognitive function deteriorates. In severe cases, hypoxia can cause seizures, coma, and death. For early aviators who often flew without supplemental oxygen, these effects were a constant and deadly threat. Even today, hypoxia remains a risk in the event of cabin depressurization, underscoring the critical importance of pressurized cabins. Cabin pressurization addresses hypoxia by maintaining a stable internal environment, with sufficient oxygen for passengers and crew. By simulating an altitude of 6,000 to 8,000 feet, the system ensures that the air inside the cabin contains enough oxygen to support normal bodily functions. This artificial atmosphere is carefully regulated, with sensors and computers continuously monitoring oxygen levels and adjusting the flow of compressed air as needed. The result is a safe and comfortable environment that allows passengers to breathe easily, even as the aircraft soars through the thin air of the stratosphere. But hypoxia is not the only physiological challenge of high-altitude flight. Another critical concern is the expansion of gases within the body. At sea level, the pressure inside and outside the body is balanced, but as altitude increases and external pressure drops, gases trapped in body cavities begin to expand. This phenomenon can cause discomfort, pain, and even injury. The most common example is ear barotrauma, which occurs when the pressure in the middle ear fails to equalize with the changing cabin pressure. Passengers often experience this as a popping sensation or temporary hearing loss during ascent or descent. While usually mild, ear barotrauma can be severe in cases of rapid pressure changes or pre-existing conditions such as sinus congestion. More serious is the risk of decompression sickness, also known as the bends. This condition occurs when nitrogen gas dissolved in the bloodstream forms bubbles due to a rapid decrease in pressure. While rare in commercial aviation, decompression sickness is a well-known hazard for scuba divers and astronauts. Symptoms can range from joint pain and rashes to neurological damage and death. Cabin pressurization mitigates this risk by maintaining a stable internal pressure and allowing for gradual changes during ascent and descent. The human body's response to high-altitude flight is a testament to its resilience, but it also highlights the need for careful engineering and design. Pressurized cabins are not just a convenience. They are a necessity, a lifeline that bridges the gap between human physiology and the harsh realities of the upper atmosphere. Without them, the dream of high-altitude flight would remain just that, a dream. Yet, the interplay between physiology and engineering goes beyond pressurization. Modern aircraft are equipped with a host of features designed to enhance passenger comfort and safety. For example, the air inside the cabin is continuously refreshed, with old air being expelled and replaced by filtered, temperature-controlled air from the engines. This not only maintains oxygen levels, but also reduces the risk of airborne illnesses and ensures a comfortable environment. Humidity control is another critical factor, as the dry air at high altitudes can cause dehydration and discomfort. While maintaining optimal humidity levels is challenging due to the risk of condensation and corrosion, advancements in environmental control systems have made significant strides in this area. The physiological effects of high-altitude flight also extend to the crew, who must remain alert and capable throughout the journey. Pilots, in particular, are trained to recognize the symptoms of hypoxia and respond swiftly in the event of cabin depressurization. They are equipped with quick donutting, oxygen masks, and undergo regular training to ensure they can handle emergencies with precision and calm. The importance of this training cannot be overstated, as the margin for error at high altitudes is razor-thin. As the third scene of this exploration draws to a close, the intricate relationship between human physiology and aviation technology comes into sharp focus. Pressurized cabins are more than just a feat of engineering. They are a lifeline, a carefully crafted solution to the challenges of high-altitude flight. They enable us to traverse the skies with ease, shielding us from the dangers of hypoxia, decompression sickness, and the myriad other risks posed by the thin air of the upper atmosphere. In the next scene, we will explore the history of cabin pressurization, tracing its evolution from early experiments to the sophisticated systems used in modern aircraft. From the pioneering efforts of engineers and aviators to the lessons learned from tragedy and triumph, the journey through the science of the skies continues, revealing the ingenuity and determination that have made air travel a cornerstone of the modern world. The history of cabin pressurization is a story of innovation, perseverance, and the relentless pursuit of progress. It begins in the early days of aviation, when the skies were a frontier and the challenges of high-altitude flight were only beginning to be understood. The pioneers of this era were not just aviators, but also engineers, scientists, and dreamers who dared to imagine a world where humans could soar above the clouds in comfort and safety. One of the earliest attempts to address the challenges of high-altitude flight came in the form of oxygen masks. In the 1920s, as aircraft began to climb higher, pilots started using rudimentary oxygen systems to combat hypoxia. These early masks were crude and often unreliable, but they represented a crucial first step. They proved that it was possible to sustain human life at altitudes where the air was too thin to breathe unaided. However, oxygen masks were far from a comprehensive solution. They were uncomfortable, cumbersome, and impractical for passengers, limiting their use to military and experimental aircraft. The breakthrough came in the 1930s, with the development of the first pressurized cabins. The idea was simple, yet revolutionary. Instead of relying on individual oxygen masks, why not create a sealed environment inside the aircraft that maintained a stable, breathable atmosphere? This concept required a complete rethinking of aircraft design, as the fuselage had to be transformed into a pressure vessel capable of withstanding the stresses of pressurization. The first successful implementation of cabin pressurization occurred in 1938 with the introduction of the Boeing 307 Stratoliner. This groundbreaking aircraft, developed in collaboration with the airline TWA, was the first commercial plane to feature a pressurized cabin. It could carry 33 passengers at an altitude of 20,000 feet, well above the weather and turbulence of lower altitudes. The Stratoliner was a marvel of its time, offering unprecedented comfort and efficiency. However, it was also a product of its era, with limitations that would soon become apparent. The true potential of cabin pressurization was realized during World War II, when the demands of military aviation drove rapid advancements in technology. High-altitude bombers, such as the B-29 Superfortress, required pressurized cabins to enable long-range missions over enemy territory. These aircraft pushed the boundaries of engineering, incorporating features such as reinforced fuselages, advanced environmental control systems, and automated pressurization controls. The lessons learned during the war would lay the foundation for the post-war boom in commercial aviation. The 1950s marked a turning point in the history of cabin pressurization, with the introduction of the first jet-powered commercial airliners. The de Havilland Comet, launched in 1952, was a trailblazer in this new era. It was the first commercial jet airliner, capable of cruising at 35,000 feet and speeds of over 500 miles per hour. The Comet's pressurized cabin allowed it to fly above most weather, offering passengers a smooth and comfortable journey. However, the Comet's success was short-lived. A series of catastrophic crashes revealed a critical flaw in its design. The square windows created stress points that led to metal fatigue and structural failure. These tragedies were a sobering reminder of the challenges of high-altitude flight and the importance of rigorous engineering. The lessons learned from the Comet disasters spurred a wave of innovation in aircraft design. Engineers began to focus on the importance of rounded windows, reinforced fuselages, and advanced materials capable of withstanding the stresses of pressurization. These advancements paved the way for the next generation of commercial airliners, including the Boeing 707 and the Douglas DC-8. These aircraft, introduced in the late 1950s, set new standards for safety, efficiency, and comfort, cementing the role of pressurized cabins in modern aviation. As the decades passed, cabin pressurization systems continued to evolve, driven by advancements in technology and a growing understanding of human physiology. The introduction of digital controls in the 1980s revolutionized the way pressurization systems were managed, allowing for greater precision and reliability. Modern aircraft, such as the Boeing 787 Dreamliner, feature state-of-the-art environmental control systems that optimize cabin pressure, temperature, and humidity, ensuring a comfortable experience for passengers and crew alike. The evolution of cabin pressurization is a testament to the power of human ingenuity and the relentless pursuit of progress. It is a story of trial and error, of triumphs and tragedies, and of the unwavering determination to conquer the challenges of high-altitude flight. Today, pressurized cabins are a cornerstone of modern aviation, enabling millions of people to travel the world with ease and comfort. As the fourth scene of this exploration concludes, the stage is set for the final chapter, a look at the future of cabin pressurization and the innovations that will shape the next generation of air travel. From advanced materials to cutting-edge environmental control systems, the journey through the science of the skies continues, revealing the endless possibilities that lie ahead. As the final scene of this exploration unfolds, the story of cabin pressurization turns toward the future, where new technologies and innovations promise to redefine the boundaries of air travel. The journey that began with the rudimentary oxygen masks of the 1920s has evolved into a sophisticated interplay of engineering, physiology, and environmental science. Yet, the quest for improvement is far from over. The skies of tomorrow hold the promise of even greater advancements, driven by the dual imperatives of sustainability and passenger comfort. One of the most exciting developments on the horizon is the use of advanced materials in aircraft construction. Traditional aluminum alloys, while strong and lightweight, have limitations when it comes to withstanding the stresses of pressurization over thousands of flight cycles. In recent years, the aviation industry has turned to composite materials, such as carbon fiber reinforced polymers, which offer superior strength-to-weight ratios and greater resistance to fatigue. The Boeing 787 Dreamliner, for example, features a fuselage made almost entirely of composites, allowing for higher cabin pressures and humidity levels. This not only enhances passenger comfort, but also reduces the risk of structural failure, ensuring greater safety and longevity. Another area of innovation is the development of more efficient environmental control systems, ECS. Traditional ECS designs rely on bleed air from the engines, which can reduce fuel efficiency and increase emissions. In response, engineers are exploring alternative approaches, such as electrically driven compressors and advanced heat exchangers. These systems promise to deliver the same level of cabin comfort while reducing the environmental impact of air travel. The Airbus A350, for instance, incorporates an electrically driven ECS that improves fuel efficiency and lowers carbon emissions, aligning with the aviation industry's commitment to sustainability. The future of cabin pressurization also lies in the integration of smart technologies. Modern aircraft are increasingly equipped with sensors and data analytics systems that monitor every aspect of the cabin environment, from pressure and temperature to air quality and humidity. These systems can detect potential issues before they become critical, allowing for proactive maintenance and reducing the risk of in-flight emergencies. In the near future, artificial intelligence, AI, could play a central role in optimizing cabin conditions, dynamically adjusting pressure and airflow to maximize passenger comfort and energy efficiency. One of the most ambitious goals for the future is the development of hypersonic aircraft, capable of traveling at speeds exceeding Mach 5. These aircraft, which could revolutionize long-distance travel, present unique challenges for cabin pressurization. At such high speeds, the external temperature can reach extreme levels, requiring advanced thermal protection systems and innovative approaches to maintaining a stable internal environment. Researchers are exploring concepts such as active cooling and regenerative heat exchangers, which could enable hypersonic flight while ensuring passenger safety and comfort. The future of cabin pressurization is not just about technology. It's also about reimagining the passenger experience. As air travel becomes more accessible, airlines are seeking ways to differentiate themselves by offering enhanced comfort and convenience. One promising trend is the use of adaptive pressurization, systems which adjust cabin pressure based on the phase of flight and the needs of passengers. For example, during long-haul flights, the system could simulate a lower altitude during sleep periods, reducing fatigue and improving rest. Similarly, during meal service, the system could optimize air quality and humidity to enhance the dining experience. Sustainability will remain a driving force in the evolution of cabin pressurization. The aviation industry is under increasing pressure to reduce its environmental footprint, and every aspect of aircraft design is being scrutinized for potential improvements. From lightweight materials to energy-efficient systems, the innovations of the future will be guided by the principles of eco-friendliness and resource conservation. The goal is not just to make air travel more comfortable and efficient, but also to ensure that it is sustainable for generations to come. As this exploration of cabin pressurization draws to a close, it is clear that the story is far from over. The skies of tomorrow will be shaped by the same spirit of innovation and determination that has driven progress since the early days of aviation. From the pioneering efforts of engineers and aviators to the cutting-edge technologies of the future, the journey through the science of the skies is a testament to human ingenuity and the boundless possibilities of exploration. The pressurized cabin, once a revolutionary concept, has become an indispensable part of modern life, enabling millions of people to connect, explore, and dream. As we look to the future, we are reminded that the challenges of high-altitude flight are not just technical problems to be solved, but opportunities to push the boundaries of what is possible. The story of cabin pressurization is a story of humanity's quest to conquer the skies, and it is a story that will continue to unfold for generations to come. And so, as the final scene fades, we are left with a sense of awe and anticipation. The skies are vast, and the possibilities are endless. The journey through the science of the skies is far from over, and the best is yet to come.